Hello, class. Welcome to an example problem for Unit 6.3 and 6.4. Unit 6.3 and 6.4 are both just sort of continuations of each other. So they're talking about equilibrium in 3D. So building off of what we learned in Unit 5.2, just doing it in 3D instead of 2D. So I prepared an example problem to go through, and it's problem 5.81 from the 13th edition of the book. And it looks sort of like, get this lined up, this guy here, where basically we have a beam that is supported at point A by a ball and socket joint, and then it has two cables connecting B to D and B to C, and then there's a 100-kilogram plate hanging from the beam there from B to A. And so I've gone ahead and redrawn this, but with our forces of interest. So we have the beam at from A to B, and because at point A it's supported by a ball and socket joint, we have reaction forces in all three directions, but no reaction moments. So I've drawn in AX, AY, and AZ. Those are all acting. Those are all forces that the ball and socket can exert on the beam. And then we have this, I've simplified this plate to just a point force acting right in the center. So that's 100 kilogram. Remember, that's kilogram, that's mass. We're going to eventually have to turn that into newtons by multiplying by gravity. And then we have the forces of these cables, tension BD and tension BC. And I've gone ahead and included all the dimensions. And what we're asked to find is the reaction forces at A and the tension in cables BC and BD. So ultimately, right, that's 5 unknowns: BD, BC, and then AX, AY, and AZ. So 5 unknowns. And a problem in 3D, we have 6 equations we can use to solve it. Sum of forces in X, Y, and Z, and the sum of the moments in X, Y, and Z. So we can solve up to 6 unknowns. In this case, we have 5, so we know it's solvable. It's just a matter of applying the right equations to make our life as easy as possible. So how can we go about solving this? So like I said, we have 6 equations, and if we are smart with how we use them, or in the case of the sum of the moments equations, where we use them, we can usually get relatively simple equations. Our goal is to try to find, or try to isolate our unknowns in our equations. If you have a bunch of unknowns in a single equation, you can't solve it, or you have to solve it using substitution or simultaneous equation solvers, which are more difficult, easier to mess up. So if I were doing this problem, what I would start with is I would say, hey, these tensions go in all three directions. That makes them kind of difficult to solve. They're going to be in almost every equation. But if I say I'm going to solve some of the moments about point B, then suddenly, because those tensions pass right through point B, they don't cause any moment. They're out of that equation. And so if I take the sum of the moments about point B, I can solve for, I can isolate some of these equations over here. So for example, if I start with the sum of the moments about point B in the Z direction, well, that has to equal 0 because we're in equilibrium. Now, because these forces act at A, from B to A, that's my moment arm, that's in the Y direction. So if I solve, AZ is going to cause a moment in the X direction. AY is going to cause no moment because it also, the line of action passes through point B. And then AX will cause a moment in the Z direction, right? So we have a Y distance, an X direction force causes a Z moment. So we know that 0 equals, and you can always do, cross product to solve this. But since there's nothing else in here, we know that the sum of this cross product of just the Z, right? So basically, I take RBA If I were to cross that with AX, so that's only going to give me a Z term. I know that AX has to be 0. So basically, I'm just doing an F times D, right? Because RB is perpendicular to AX, I can just multiply them directly together. But you could write out the whole cross product if you wanted to. Okay, so AX equals 0. So that's one of our unknowns. So next I'm going to do sum of the moments about B again. But I want to find AZ. So to do that, I know AZ is going to cause a moment about the X axis. I'm going to say the sum of the moments about point B in the X direction has to be 0. And that's going to give me the R, the A again, crossed with AZ. It's going to be, and although in this case, I also have this weight here. So it's plus minus 1J crossed with negative 100, which 9.81. Okay, right. So that's the distance from point B to where this force acts, and crossing that with the mass of the plate times gravity. And if I do my math out, I end up getting 0 equals negative 2 AZ plus 900. And 81. Right, and if you want to kind of convince yourself, AZ is going to cause a negative X moment, so mass is going to cause a positive Y. So okay, the signs do make sense, and of course, if you just do the cross product, you'll get there. And so then I can solve for AZ equals 490.5 newtons. That's unknown number 2. All right, so now we get to the more difficult part. The sum of the moments about B at least doesn't do me any more good because I can't solve for AY that way. So now I'm going to jump into using my sum of my forces equations. So first thing I'm going to do is I'm going to find the unit vectors for TBD and TBC. I know I'm going to have to use those. So I'm just going to find them. So I have R BD equals minus 2. I have to walk minus 2 in the X direction. I have to walk minus 2 in the Y direction and plus 1 in the Z direction. And the unit vector is 2, 2, 2, 2, 2, 1. The magnitude that's going to be 3. So the unit vector is minus 2/3. Minus 2/3. Plus 1/3. All right, so I'm going to let's see, we'll call that 1. We'll use that later, and then do the same thing for RBC. 1 and a positive 1 in the X, minus 2 in the Y, and positive 2 in the Z. That's going to have the same magnitude, so unit vector would be C 1/3 minus 2/3 J plus 2/3. All right, hopefully you're with me so far. So I am going to start with let's see, which big space. Sum of the forces in X equals 0. So I'm going to look at all my X's, and I know my my reaction force, and I'm starting with this because my reaction force in X is 0, I already know. So sum of forces in X equals 0. I get 0 equals, let's see, so the tension in BC, which I don't yet know, times the X component of the unit vector, so 1/3. And that's positive, and then minus PVD, and its X component is 2/3. So I can say PVD equals 1/2 PVC. All right, so that's the relationship. They're constrained by that relationship. TBD must be 1/2 of whatever TBC is. So that's as far as that equation is going to get me. So let's go to the sum of the forces in X. Or sorry, sum of the forces in Z, rather. So with Z, I get 0 equals, and so I have the weight of the plate, so minus 981. Then I have plus TBCZ plus TBDZ plus AZ. All right. So now I'm going to say, going to say that, using, should have done this before to be more on this equation to be more exact, but using 1 and 2 and subbing 3. I'm going to rewrite this a little bit, so I get 0 equals minus 981 still. And then I get plus TBC, and the X part of TBC, so that's 2/3, plus, and then TBD, remember, is same as 1/2 TBC, and its Z part is also, right, yeah, so it's 1/3, and then AZ is 495. So I add like terms together, and I can get to 5, 6 TBC equals 490.5. That gets me that TBC equals 588.6 units. Okay, now I can just say, what I call this, 4, I can say sub 4 into 3, and I can get TBD equals 294.3 newtons, right? Since I know TBD is 1/2 of TBC, as defined by my equation number 3. So now I have my 5 unknowns. All I have left to find is a y, which I can find using my sum of my forces in y now. So sum of forces in y equals ay plus tbcy plus tbdy. And so I say subbing 1 and 2, and I get that 0 equals ay plus 588.6 times minus 2/3, so TBCY is going into minus YA, like TB. Yes, yes. Oh, gotta keep my direction straight. TBCY is going to the minus Y direction, and then plus 294.3, also going in the minus Y direction, minus 2/3. And I get that AY equals 588.6 meters. Okay, so hopefully that's helpful. I guess I just want to reiterate the important things to do is, draw your free body diagram. You want to draw all of your reaction forces in your free body diagram. I know my head's not quite here. And again, the reaction forces or moments, just you can think of them as the ways that reaction can resist motion, the directions that thing's going to resist motion. So because that's a ball and socket, if I pull and yank on it or try to shear it, it's going to not let me. But it will let me rotate freely, so there's no reaction moments. So you're going to draw those in. I always draw them in the positive direction, and then I just know that if I get a negative answer in after I solve it out, that I just drew the arrow the wrong way. But I draw the arrow in the positive direction, and I just assume that that's the direction it is in my math. And for each, in a 3D problem, you can solve it for 6 unknowns because we have 6 independent equations that are available to use. And then you do the math, right? You try to pick the equations that make your life easiest. And then it's just building off principles we already know. So hopefully you find that helpful for unit 6.3 and 6.4. And as always, if you have more questions, feel free to reach out to me, email me, message me, text me. I'm always available. And hopefully you have a great time this unit and have a lot of success preparing for exam number 2 coming up.